So we're just going to talk about how we can solve exponential equations and use logs. We've solved exponential equations before, but with some of the examples that we had, we got to a certain point where we couldn't actually solve it using the method we had, which was simply getting the same base on either side and equating the powers. So if you're trying to solve an exponential equation, firstly, check whether you can get equal bases. Because if you can on either side, then you can just equate the powers. So that's the first thing you're going to do. Now when they cannot be established, and sometimes they can't, then you have to log both sides. And logging both sides will enable you to be able to solve that exponential equation, whatever it is, if it can be solved. You also sometimes have to look out for other factorization patterns. But we're going to talk about some examples, and that's all going to start making a lot of sense. So we just need to remember the one rule that we've got about logs that's really important, and that's this rule here. Now we're going to use different rules throughout, but remember that if you've got log base a of a to the x, that's actually just equal to x. So how does that help us? Well, the whole point of these questions is we're trying to get x on its own. We're trying to stop it from being a power and make it an actual value. So if we get 2 to the x equals 14, what we can do, as long as we do it to both sides, is to log base 2 to the x. So I'm going to log base 2 to the x, and I'm going to go log base 2 of 14. I've just logged both sides with the base of 2. And so I know from this rule up here, I know that's just going to leave me with x equals log base 2 of 14. Now I can easily put that in my calculator and get a value for that in terms of decimals, but I can't actually make it any simpler without doing that. So I'm just going to leave it like that. There's actually another method I can do it with, and this method I've done right now here is the simplest, but basically I can log base anything. So what I mean by that is I can use any base, any log base, as long as I do it to both sides. So if I go log base 10 of 2 to the x, I can say that equals log base 10 of 14. I could do log base 20, log base 50, it doesn't really matter. Then I can use the law that allows me to multiply down by that power. And so I'm going to write in a different color, x log base 10 of 2 equals log base 10 of 14. And so my final answer is I'm going to divide log base 10 of 14 by log base 10 of 2. Now you might think, well, how can you do that? Log base 10 of 2 is just a number. You put that in your calculator, you get a decimal. So I can divide by it, I can multiply by it, that's okay, as long as I keep it together. Now you might look at that and go, well, that is not simpler than that. And you're completely correct, it's not. But what it does help us to see is it helps us to see a certain identity that always works with logarithms. If we look at this bit, we've worked out x here, and we've worked out x here. So hopefully you're happy for me to say then that if x is equal to x, that has to equal that. So that tells me that log base 2 of 14 equals log base 10 of 14 over log base 10 of 2. Notice this and this and that and that. And that's actually an identity that holds across logs. If I've got log, and this is worth writing down because we might not have talked about it, if we've got log base a of b, that is equal to log base c of b over log base c of a, where c is just a number. It doesn't have to be 10, could have been 7, could have been 8, I just chose to use 10. So that's just an interesting identity that works with logarithms. Okay? But if we're just trying to solve this equation, this method up here is probably the simplest way of going about solving it. Now here we've got 5 to the 3x take 5 equals 37. Okay, so we're just going to simply solve this, and we're going to go straight into one method. We're not going to log base 10 it, because there's no need to, so I'm going to go 5 to the 3x take 5 is equal to 37. I'm going to log base 5 on both sides of 5, 3 to the x take 5 equals log base 5, 37. And so therefore I'm going to get 3x take 5 is equal to log base 5 of 37, and I'm going to rearrange this equation like I would any equation because I know that log base 5 of 37 is just a number. So I'm going to add 5 to both sides, so I'm going to get 3x equals log base 5 of 37, add 5, and then I'm going to divide both sides by 3. And so I'm going to get that x equals log base 5 of 37 plus 5 divided by 3. And that's the answer to my question. Okay? Hopefully that makes sense. I'm running out of room over here, so I'm going to sneak over to the side, but hopefully you've managed to write a bit smaller than I have. This one's a little bit different. We've got 5 times 3 to the x equals 15 over 20 root 27. Before we go straight into it, hopefully you can see that those numbers are sort of all related to each other. And you should be able to see that 5 is an actual multiple of 15. What we want to do is be able to get one side of the equation into the other side of the equation where the left-hand side, or it doesn't really matter if it's the left-hand side or the right-hand side, but we want it written as a base raised to a power, something like a to the b. And currently we don't have that. We've got 5 times a to the b. So we want to get rid of that 5, and we can simply do that. It's 5 times 3 to the x. We can divide both sides by 5. So if we divide the left-hand side by 5, we're just going to be left with 3 to the x. I'm going to divide the right-hand side by 5 as well, so I'm going to get 15 over 5 times the square root of 27. Now hopefully you can see that 15 divided by 5 is 3, so I can go that's equal to 3 to the x over 3 square root of 27. Now this is where you need to get a little bit familiar with powers of 3, powers of 4, because you should be able to look at 27 and recognize that 27 is actually 3 to the power of 3. Now that's interesting because if I'm looking at this, I could go into solving using logs, but I could see if I can actually solve this on my own without using logs. So if I've got 3 to the x, now I've got everything on the right hand side which is written with a base number of 3. So surely I'll just be able to equate power. So that's going to be 3 to the x equals 3 over, well, we've got the square root of 3 to the 3, so that's actually 3 on 2. And so 3 to the x, if we apply log laws, index laws, we've got 3 to the 1 divided by 3 to the 3 on 2, so that forms 3 to the negative a half. And so therefore, if we just equate bases, equate powers, you get x equals negative a half, and that's the answer to that one. Okay, so that one we didn't actually have to use logs, and that's where the point 2 comes in. Or point B, you don't always have to use logs if you can equate the bases. Now this one looks a bit different, and this one should start ringing bells. Remember with exponential equations, some of the ones we solved, we could actually factorize them. And the thing that gives you a hint that you could potentially factorize is when you've got separate terms. So up here, if we look at this one up here, we don't have separate terms. We've got a left-hand side equal to a right-hand side and one term on each. Yes, we've got separate terms in the powers, but we don't actually have separate terms with different base numbers. Down here, again, we've got a left-hand side equal to a right-hand side and one term. 5 is multiplied by 3 to the x, so we can get rid of the 5 by dividing, but we don't actually have separate terms. Here, we've got two separate terms. We've got this term and that term. Now, if you think about it, 4 to the x can be written as something else. It could be written as 2 to the 2x, couldn't it? And then hopefully you can see, well, that can be written as 2x squared. Interesting. 2 to the x plus 1, how else can you write that? Well, remember, if you've got those powers added together, that comes from having two things multiplied together. That comes from having 2 to the x multiplied by 2 to the 1. Okay, so I'm just going to write it like that because that's going to help me factorize. So I'm going to get 2 to the x squared plus 2 to the x times 2 to the 1 equals 15. Now that might still look a bit ghastly, but hopefully you can see there that now I've got two bases, the same base in each term, one's squared and one's just multiplied by 2. So could I not do what I did before and go, well, let a equal 2 to the x? Now, it depends where you want to do this. You might want to just work over here. So if I go let a equals 2 to the x, and I'm going to work over here, I'm going to get a squared plus 2a equals 15. Now I can say, well, that's really a squared plus 2a take 15 equals 0. If you're not sure how to factorize that, put it in your calculator. But hopefully you can see pretty quickly that that's going to be a plus 5 times a take 3 is equal to 0. Because the factors of negative 15, 5 and negative 3, when added together, will give you 2. So we've got that now. A plus 5 times a take 3 equals 0. That tells us now, if we go back to here, that we can replace the a in our brackets, we replace it by 2 to the x. So instead of having a plus 5 times a take 3, we get 2x plus 5 times 2 to the x. 2 to the x plus 5, I should say. 2 to the x plus 5 times 2 to the x take 3 is equal to 0. Now, we're going to get two answers, and again, I apologise for running out of space, and I'm just going to head down here so I have a bit more space. So I'm either going to get 2 to the x plus 5 equals 0, or I'm going to get 2 to the x take 3 equals 0, and they're my two potential answers. 2 to the x therefore equals negative 5, or 2 to the x equals positive 3. Now you can graph 2 to the x, but one thing you should note from that, and remember with an exponential equation, if you've got something a to the power of x, the asymptote of that one is at 0, and so this graph is, and this number is positive, so this graph is actually completely above the x-axis. If you're not sure about that, you can graph it in your calculator. Graph y equals 2 to the x. So 2 to the x is actually greater than 0 for all x. So that solution, this part is not going to give you anything. So you can write it like that. That little thing means for all. And so we get 2 to the x equals 3. Now how do we solve that? Well, this is where our logs come in, because we can just go log base 2 of 2 to the x equals log base 2 of 3. So x is equal to log base 2 of 3. Beautiful. Done. Okay, that is our one answer that we can have for that question. We could do it using log base 10, but I'm just going to do it that way. Alrighty. So now we've got two more questions. We want to solve this equation here. We want to solve the equation that negative 3 times 2 to the x plus 5 plus 6 is equal to 5. And remember, when we're solving equations, we really want to get a base number raised to a power equal to one number. So we just want to rearrange this equation first to start with, like we would any equation. We want to get 2 to the x on its own. So I'm going to take 6 from both sides, and I'm going to get negative 3 times 2 to the x equals negative 1. Then I'm going to divide both sides by negative 3, so I'm going to get 2x equals 1 over 3. Negative divided by negative is a positive. Alrighty. Now, can we solve that? Well, yes, of course we can, because we know that we can use logs. So we can go log base 2 of 2 to the x equals log base 2 of a third, and therefore x equals log base 2 of 1 over 3. So we've now got the ability to solve all exponential equations that we get thrown. Now we get asked to graph the left-hand side of that equation. We want to graph y equals negative 3 times 2 to the x plus 6. Okay? So we're going to graph y equals negative 3 times 2 to the x plus 6. Alrighty. Now, to graph, remember, I'm a little bit fussy on graphing, but one, you need asymptotes, and two, you need intercepts. These sort of graphs, really quite straightforward to graph. You can simply chuck that in your calculator and get the y-intercept and x-intercept off it. But I just want to do an example of actually finding it by hand, because it's not going to be that hard. hopefully you can look at that graph and recognize that this bit is the asymptote. Okay, you need to know that. You need to know that with the format of a graph. If you've got a general form of something of the form of a, and it doesn't matter what letter you use, but b to the x takes c plus d, that d in there is our asymptote, okay, and you should know that one. However, what we can also do, so we know that is our asymptote. We know our asymptote occurs at y equals 6. Let's also find our intercept. So our y-intercept, of course, that's going to be when x equals 0. So in this case, it's going to be y equals -3 times 2 to the 0 plus 6. And then whenever you're subbing in that as 0, you're going to make that 1, that base raised to the power, that's going to become 1. That index is going to become 1. So you're going to get y equals -3 plus 6, which is equal to 3. And so therefore, it becomes 0, 3. That's your y-intercept. Your x-intercept is when y equals 0. So you're going to get the equation -3 times 2 to the x plus 6 equals 0. Very similar to the equation we just solved over here, except this one was equal to 5. This one's equal to 0. So if we think about that now, we're just going to solve that equation. We're going to get -3 times 2 to the x equals -6. You're going to get 2 to the x is -6 divided by -3, which is 2. And so we're going to go log base 2 of 2 to the x equals log base 2 of 2 to the 1. Oh, this is going to give us a nice answer, because this side becomes x and this side simply becomes 1. So in this case, we get a really nice answer by solving it using logarithms. And so our x-intercept is 1, 0. So now when we're drawing it, we just have to make sure we put our y-intercept in the right spot, our x-intercept in the right spot, and we draw our asymptotes in correctly. So axis, nice arrowheads everywhere. Okay, arrowheads. Label y, x. If it's an application question and you've got a context, make sure you label it. 1, 2, 3, 4, 5, 6. I'm going to put 0 down there, and I'm going to 1, 2, 3, 4. I'm going to put a 6 up there. And then I'm going to label my x-intercept. So my x-intercept is 1, 0. There. I can put a label on it. And my y-intercept is 0, 3. Up there. Put a label on it. And so I can draw my graph. Now, in this case, we haven't been told that it can't be less than 0. And it, by the looks of it, it's going to be, isn't it? It's going to go in a certain direction. So you should know from that negative here that the graph is not going to go that way. It's actually going to go that way. Okay, so you should know that if you know stuff about the shapes of the graph. I'm just going to erase this bit over here because I'm running out of room. Alrighty, nice. So we've got 1, 0, and we've got 0, 3 up here, and we've got a nice graph. And we're just going to draw our graph. So mine might be a little shaky, but you should be able to draw yours nicely. Make sure, as you remember, that we make it look like it's an asymptote. We also want to make it look exponential. I've seen some really straight exponential lines over the last few weeks. It's an exponential line. It needs to look exponential. And there you go. Now remember, draw graphs in pencil so you can erase them and have another go. But there you go. We've done it. Exponential equations using logs.